Hi again. In this PowerPoint, we will discuss on introduction to Fourier series, and you might need to refer to your basic calculus to help you understand more on this topic. We know previously that a square wave signal is a periodic signal which consists of sinusoids and its harmonic. The question is now, how are we going to model this function, or in other words, what is the equation that describes this signal? We know that the square wave below is a periodic function. This periodic signal can be modeled with a combination of sines and cosines as shown here in equation 0. In order to describe the function analytically, we need to find coefficients ai and bi in this equation. In order to determine the coefficients, let us recap on integrals for sine, cosine, and product of sine and cosines. These fundamentals are important to help us understand the concept of Fourier series expansions. First, let us define the integrals for sine and cosine. Based on equation 1 for integral of sine, we have integral of sine mt dt for 0 to 2 pi equal to 0. And in order to understand that, we add 1 over m before the integral and minus m after the integral. And after the integration, we have minus 1 over m cos mt for a period of 0 to 2 pi. This will give us 1 over m times cos m 2 pi minus cos 0. Both will give us 1, and therefore this equation equal to 0. To illustrate for equation 2, the same thing goes for equation 2. We add 1 over m before the integral and minus m after the integral time cos mt dt. After the integration, we have 1 over m sin mt for a period of 0 to 2 pi, and this will give us 1 over m sin m 2 pi minus sin 0. Both sine will give us 0, therefore these equations end up with 0. To go further, let us look at integral of sine times cosine. And in this equation, integration of sine mt cos nt dt for 0 to 2 pi will also give us 0. To illustrate this, let us look at the integration of sine mt cos nt dt for 0 to 2 pi. If you can recall the trigonometric equations based on the table that I highlighted in red, we have equation number 3, which says here sine A times cos B equal half sine A plus B plus sine A minus B. And we put that into our equation. So our equation will be integration of half sine m plus nt plus sine m minus nt dt for a period of 0 to 2 pi. If we recall, for any integer, this equation is the same as in equation 1. Therefore, both terms, left and right, will give us 0. Now let us look at the integral of product of sines. If we integrate product of sine mt times sine nt, based on the trigonometric identity table provided here, we can rewrite the equation into integral of half cos m minus t minus cos m plus t dt for 0 to 2 pi. For this integration, there are two possibilities, and I put it here as case 1 and case 2. Case 1, if m not equal to n or m not equal to minus n. We elaborate further for the integration above. So we have that for case 1, both terms left and right equals to 0 since cos m plus n t dt is equal as equation 2 where the results is equal to 0. For case 2, when m equal to n, and if we rewrite the integrations, we have half integral of cos m minus n dt minus half integral of cos m plus n t dt, which results in the left hand side of the term will remain as 1, and finally we have the value is pi. So if we recap, when n equal to m, the integration of sin mt dt is equal to integral of sin square mt dt, where the result is pi. Moving forward, let us look at the integral of product of sines. The same things goes for product of sines just as in the previous slide. If we integrate cos mt cos n t dt based on a trigonometric identity as enclosed in the box, it will give us integrals of half cos m minus t plus cos m plus tt dt. Again, we have two cases. First is if m not equal n or m is not equal to minus n. When we integrate both terms, any non-zero integer is equivalent to equation 2. Therefore, both terms for left and right equals 0. In case 2, where m equal to n and m not equal to 0, when we integrate both terms, the first term when m equal to n will give us cos 0t, and the second term cos 2m will give us 0. So therefore it leaves us only integral of cos 0t dt, and the value is pi. So for case 1, the integral of product of sine when m not equal to n or m not equal to minus n, the value is 0. For case 2, when integer m is non-zero integer and m equal to n, we have integral of cos square mt dt, the value is pi. Now that we have the integrals, let us go back to equation 0 and try to find the coefficients. So in this case, we'll look at coefficient a0. To solve for a0, let's take the definite integrals of both sides of the equation from 0 to 2 pi. We rewrite for sum of definite integrals for each term and apply the integrals equation 1 and equation 2 that we derived from previous slide, and it leaves us only integral of ft dt equal to a naught integral dt, which equal to a naught 2 pi. And finally, we have our a naught equal to 1 over 2 pi integral 0 to 2 pi ft dt, and this value is actually equal to average value of ft over 0 to 2 pi. In this slide, let us walk through finding Fourier coefficients for the cosine term. From the basic equation 0, let us multiply both sides by cos nt and the integrals over 0 to 2 pi. Based on equations 1, 2 and 3, most of the elements on the right hand side are 0, leaving us only integral of an times cos nt times cos nt, which equals to an integrals of cos square nt dt. If we recall, integral of cos square nt dt from equation 7, the value is pi. Therefore, substituting this value, our an will be an equal 1 over n integral of ft cos nt dt from 0 to 2 pi, and we name this as equation 9. To find Fourier coefficients for the sine terms, let us multiply both sides by sine nt and the integrals over 0 to 2 pi. Again, based on equations 1, 2 and 3, most of the elements on the right hand side are 0, leaving us only integral of bn times sine nt times sine nt, which equals to bn integrals of sine square nt dt, which, if we recall, equal to equation number 5, leaving us the equation of bn equal 1 over pi integral 0 to 2 pi ft sine nt dt, and we name this equation as equation 10. This slide shows the summary of integrals that we discussed in the previous slides. We will have to refer back to these equations when we discuss about finding Fourier series coefficients in next few examples. What is trigonometric Fourier series? The trigonometric Fourier series is an example of generalized Fourier series with sines and cosines substituted in as the orthogonal basis set. If signal ft is periodic with period t, then ft can be expressed as a Fourier series as shown in equation 0 that we referred earlier. So our ft will be a0 plus a1 cos 2 pi f0 t plus an cos 2 pi f0 n t plus b1 sin 2 pi f0 t plus b2 sin 2 pi 2 f0 t plus bn sin 2 pi n f0 t. Or compactly, we can also rewrite into these two equations. 1 ft equal to a0 summation of n equal to 1 to infinity bracket an cos 2 pi n f0 t plus bn sine bracket 2 pi n f0 t. Or in terms of omega, ft equal to a0 plus summation of n equal to 1 to infinity bracket an cos n omega naught t plus bn sine n omega naught t. If we put back together, the coefficients for the Fourier series can be summarized as below. The term a0 is the constant or the DC component defined as a0 equal 1 over t integral 0 to t ft dt, or a0 equal area over 1 period over period. The coefficients for an and bn are an equal 2 over t integral 0 to t ft cos n omega t dt, and bn equal 2 over t integral 0 to t ft sin n omega t dt. Replacing t with 2 pi, we can also rewrite an equal 1 over pi 0 to 2 pi ft cos n omega t dt, bn equal 1 over pi integral 0 to 2 pi ft sin n omega t dt. The limit can be from 0 to t, or 0 to 2 pi, or from minus t over 2 to t over 2, or minus pi to pi. In electrical engineering, Fourier series of functions is for odd symmetry, f minus x equal minus fx, in which a function is odd if it is inversely symmetrical about the y-axis. The average value of an odd function is always 0, therefore a naught equal to 0. The Fourier series contains sine terms only, therefore the equation for the Fourier series for odd symmetry waveform is ft equal summation of n equal to 1 to infinity bn sine n omega t. The figures in this slide show some examples of odd symmetry waveform. For even symmetry, the equation f minus x equal fx, and the functions are even if they are symmetrical about the y-axis, and the common example is for cosine function. The Fourier series contain cosine terms and also a constant a naught. Therefore, the Fourier series equation for even symmetry signal is given here. Ft equal a naught plus summation of n equal to 1 to infinity an cos n omega t. The figures below show examples of even symmetry waveform. The half-wave symmetry is where that the second half of the wave is exactly opposite to the first half. The equation ft equal minus ft minus t divided by 2, or ft equal minus f bracket t plus t divided by 2. Only odd harmonics with n equal to 1, 3, 5, 7 are present in the series. Odd functions with half-wave symmetry contains odd harmonics sine wave terms. Even functions with half-wave symmetry contain odd harmonics cosine wave terms. Functions neither odd or even contains both odd harmonics sine and cosine term. For half-wave symmetry, the coefficient a naught and b naught are 0 for even harmonics with n equal to 2, 4, 6, and so on. Examples of even symmetry waveforms are shown in figure below. More examples of even and odd functions are shown in the next two slides. Example of odd and even functions. 1. Cosine x and sine x. Another two example for even function x minus t equal to xt. One-sided forms have only cosine terms. An odd function x minus t equal minus xt. One-sided forms have only sine term. In the next PowerPoint presentation, we will go through some examples in finding Fourier series for some periodic signals. Thank you.